Hello to everyone. I would like to thank the organizers for inviting me for delivering this talk. The title of my talk is A Phase Transition Characterized via a Chaotic Diffusion for Two-Dimensional Mapping. My name is Edson Denis Leonel. I am professor of physics in São Paulo State University at the city of Rio Claro in Brazil. The goals of my talk are discuss a phase transition from integrability to non-integrability in a two-dimensional mapping. And for doing that, we have to answer a specific set of four questions. First, we have to identify what is the broken symmetry in the problem. Second, we have to define the order parameter. Third, discuss the elementary excitation. Finally, four, discuss the topological defects which impacts in the transport of particles. We start with, let us consider a Hamiltonian function of this type, which is composed of two forms. One of them is age naught, and a second one is age 1. Age 1 is controlled by a counterparameter epsilon, which controls a transition from integrability to non-integrability. Of course, when epsilon equals to 0, the system is integrable and depends only on I1 and I2, which are action variables. And when epsilon is different from 0, there is also a set of two new variables, theta 1 and theta 2, letting then the Hamiltonian to be non-integrable. Since this Hamiltonian is time independent, the energy is a constant, and we may take some advantages of this to eliminate the variable I2 from the expression of the arguments and then rewrite the Hamiltonian in terms of only three dynamical variables I1, theta 1, and theta 2. This leads to a three-dimensional flux of solution, and that may be intercepted by a plane, and the set of points crossing the plane generates a set of points described by a two-dimensional mapping. And this plane is called the surface of Session or Poincaré Session, and the dynamics is mostly described by a generic mapping of this form, which relates variable in and theta n to in plus 1 and theta n plus 1. And there are three functions which are nonlinear functions of their dynamical variables: h, capital K, and p. So, since this mapping comes from a Hamiltonian, it must preserve the area in the phase space. Then the determinant of the Jacobian matrix must be equal to the unity, and this is fulfilled when the following condition is observed. Derivative of p with respect to theta n plus derivative of h with respect to in plus 1 must be equal to 0. Although we don't know what are the analytic functions for this case yet, this relation must be fulfilled to guarantee area preservation of the dynamics of the mapping. For this presentation, we will consider as fixed age as a sign, p as a 0. This is only to eliminate the counterparameter from the second equation for the dynamical variable theta. And finally, capital K defines a family of a function which is written as 1 over absolute value of in plus 1 to a power of gamma. Gamma is a non-negative number, and interestingly, this expression, when substituted in the mapping, gives a mapping of this form. The determinant of the Jacobian matrix of this mapping is equal to the unity. The area is preserved. Interestingly also, when capital in plus 1 is small enough, this expression 1 over capital in plus 1 to a power of gamma is large, and because of this modulo 2 pi, theta n becomes uncorrelated to theta n plus 1 in the limit of large fraction, and this uncorrelation makes this sine function becomes works like a pseudo-random function, leading to diffusion on this dynamical variable I. However, when capital I becomes large, this ratio becomes small, bringing correlation to the dynamical variable, and this correlation brings regularity to the phase space. A typical plot of the phase space for this mapping is shown here in this figure. For the control parameter epsilon equals to 10 to the power of minus 3. We see here two curves plotted in red defining the invariant spanning curves, a large chaotic C, which is characterized by a positive Lyapunov exponent, and a set of periodic islands, mostly known as Kolmogorov-Arnold-Mozart islands. Of course, when epsilon equals to 0, the system is integrable because in plus 1 is equal to in, and the phase space is mostly plotted as a set of curves parallel to each other, which defines a foliated phase space, which has this shape here. So this first plot, which I define as figure A, is for integrable case, while B is for the non-integrable case where we have chaos. Of course, the symmetry is destroyed. The symmetry which is broken here is the symmetry marked by these parallel curves due to the integrability, leading then to a chaotic diffusion for epsilon different from 0. The broken symmetry is then, of course, this destruction of the parallel curves, parallel lines, foliated phase space, turned into this mixed phase space. Of course, the chaotic diffusion is not allowed to diffuse unbounded due to the existence of these two invariant spanning curves, which work as barriers blocking the passage of particles through them. This is mostly defined or mostly played by the Liouville's theorem, which guarantees area preservation on the phase space. The chaotic C is, of course, limited by these two invariant spanning curves. The negative one is given by gamma epsilon over 0.9716, which has an implication to be here, which is obtained from a transition from global to local chaos in the so-called standard mapping, and this expression to a power of 1 over 1 plus gamma. And the positive one is symmetric to the negative side, which has the same expression. Then the order parameter. Let us think about what could be defined an order parameter for this problem. A first observable, which is a candidate to define the order parameter, would be the Lyapunov exponent. But I will argue that Lyapunov exponent is not a good dynamical variable to define an order parameter, because in statistical mechanics, when we face a second order phase transition, the order parameter must go continuously to 0, while the susceptibility of this control parameter must diverges in the same limit. And when we see here in this plot, the Lyapunov exponent obtained for the positive side, for the positive Lyapunov exponent, indicating chaos on the phase space, as a function of the parameter epsilon, we see here there is a set of 4 orders of magnitude in the control parameter epsilon, and the Lyapunov exponents varies very little, only from the order of 15%. So the phase space indeed birth as chaotic, as mixed, leading to a finite diffusion of these chaotic dynamics. So we don't see here the Lyapunov exponent coming continuously to 0. So the Lyapunov exponent is, I'm afraid, not a good dynamical observable to characterize an order parameter. But instead of this Lyapunov exponent, a good candidate is I root mean square, which defines a dynamical variable for the diffusion, for the chaotic diffusion along the phase space. And because the phase space is symmetric from positive side to the negative side, the average action is not a good variable, but rather the squared action is a good one. So to define I root mean square, we take two different averages. 1 over n summation when j varies from 1 to n gives an average over the orbit, while 1 over m, capital M, summation 1I varies from 1 to m gives an average over an ensemble of different initial conditions. And the curves plotted in log-log plot of I root mean square against n reads mostly like this. For initial action very small, typically close to 0, we see the curves start to grow with n in a parallel shape, and then eventually they bend towards a regime of saturation, which is marked by this constant plateau. The red symbols correspond to epsilon to a 10 to a power of minus 4 whenever the circles are corresponding to a parameter epsilon 10 to the minus 3. And, and these curves also work well when initial action is different from 0. I selected two initial actions different from 0 to argue this in scaling invariance, typically observed in second order phase transition, also works well for different initial action. Well, the saturation, which is observed for long enough time, is given by an I sat proportional to epsilon to a power of gamma. Gamma is so-called the critical exponent. The regime of growth is marked by I root mean square proportional to n epsilon squared to a power of beta. Beta is called an acceleration exponent. And then finally, for I naught approximately to 0, this relation here gives beta from the order of half, which typically characterizes random walk particles, and then the crossover interaction number, which marks the changeover from the regime of growth to the saturation, is given by an epsilon to a power of z. For the mapping, remember this mapping here, we have critical exponent alpha 1 over 1 plus gamma, which was obtained in previous publication. The critical exponent c is given by minus 2 gamma over gamma plus 1. And then we now have a candidate for the order parameter. So if we see here, we are characterizing chaotic diffusion. I sat, which marks the value of the action leading to the saturation, depends on the parameter epsilon to a power of alpha. And since gamma is a non-negative number, this I sat goes continuously to 0 when epsilon approaches 0, which is the limit of control parameter, which marks the transition from integrability to non-integrability. So the first part of a characterization of a phase transition is fulfilled by this condition here, so defining I sat as a candidate to an order parameter. Let us now discuss analytically what happens to these curves when we approach the chaotic dynamics for considering it as Brownian motion, Brownian particles moving along the chaotic dynamics. So solving the diffusion equation depends on diffusion coefficient T, which is obtained from the first relation of the mapping from the phase equation. P, capital P, gives the probability to observe a given particle with an action I at a given time n. And just remembering, this probability gives a position along this chaotic C, because the chaotic dynamics is confined to move only along in these two invariant spanning curves. So the chaotic diffusion is confined between minus I Fisk. Fisk is the acronym for first invariant spanning curve. and imposing the following boundary conditions: derivative of p with respect to I evaluated at plus minus I fisc equals to 0, which physically implies there is no flux of particles through the invariant spanning curves, not violating the Liouville's theorem. Also considering the initial condition uh, concentrated as a delta function, a probability to observe a given action at initial time is a delta function. The technique considered here was a separation of variables, which gives a probability of this type. There's a summation from k varying from 1 to infinity, and this summation, which is also uh, dependent on epsilon, on exponential with negative argument, goes to 0 when n goes to infinity and also the k grows. This term here, so this goes to 0 for large enough k and large enough n. We have then a term which marks the saturation, and then the dynamical variable we are looking at is I squared, which is integral from minus I fisc to plus I fisc, I squared pi di, which gives this very nice expression, which I'm not showing here the details, but we'll only concentrate on the main results. So the symbols give the numerical simulation whenever the constant lines give the analytical results obtained from the square root of this expression here. Finally, to prove scaling invariance, which is typically from phase transitions, second order phase transitions, if we rescale properly the axis, both the vertical and the horizontal one, all the curves overlap each other onto a single and hence universal plot, as typically observed in second order phase transitions. So the second order phase transition, which is the second question we have to answer in this seminar, is I sat proportional to epsilon to a power of alpha. So we note that in the limit of epsilon coming to 0, the order parameter approaches continuously to 0. The susceptibility of this order parameter I sat is then derivative of I sat with respect to epsilon, which is the nonlinear parameter controlling the amplitude of this sine function, is written on this form. We see here that since gamma is a non-negative number in the limit of epsilon approaching to 0, this susceptibility diverges, it goes to infinity. Then this is a clear signature that the second order phase transition, the transition from integrability to non-integrability we are facing in this family of error-preserving mapping, is a second order phase transition. Let us now move and try to argue on the third question, which is discuss the elementary excitation. To start with, we remember the mapping is written on this form. There is an epsilon sine of theta, and then epsilon sine of theta will marks indeed the amplitude of the nonlinearity. Epsilon is the amplitude of the nonlinearity. If we think about the chaotic dynamics along this chaotic sea, is remembering as stochastic dynamics. It could be described in well form, as I proved in earlier slides, with the well overlap of the curves obtained from numerical simulations iterated from the map, overlapped with the curves obtained from the analytical solution of the diffusion equation. So a particle moving along this chaotic sea has probability to increase the action or even to decrease the action. Probability P to increase, probability Q to decrease. And then the average step size a particle is moving up or down is epsilon over square root of 2, then which is proportional to epsilon. So the elementary excitation of this problem is, of course, the own control parameter epsilon, which controls the amplitude of the nonlinearity sign. Finally, the topological defects, which impacts in the transport of particles. Well, to discuss this problem, I'm plotting here again the phase space. We see here the two invariant spanning curves. For the first plot, epsilon 10 to a power of -2. For the second one, epsilon 10 to a power of -3. The scaling, the scale of the phase space changes, but well, the main message is that invariant spanning curves also, which blocks the passage of particles through them. So the phase space also exhibits periodic islands. And these periodic islands are centered by elliptic fixed points. And the transport of particles are the survival probability for particles moving only along the chaotic dynamics are described by exponential functions. So we see here two red curves, which are curves defined in the following sense. If we give an initial condition along the chaotic sea and let the dynamics to evolve, if the particles survive these dynamics, so the curve is plotted as red. We see here the beginning of the curve is described by an exponential function, and then later on the curve is slower, the decay changing from a power law. So the blue curves also show the exponential decay, and then a slower one. The slower one is, of course, marked by particles which stay trapped near these periodic islands, defining then a dynamical regime which is called stickiness. So stickiness are observed by temporary trapping of particles near the periodic islands, and these periodic islands are generated from the elliptic fixed points, which are considered then the Kolmogorov-Arnold-Mozart islands are then the topological defects that impacts on the transport of particles along the phase space. So to conclude my seminar, we studied a phase transition from integrability to non-integrability, and our observables allow us to conclude the transition observed is a continuous phase transition, since the order parameter goes continuously to zero. At the same time, its susceptibility diverges at the transition. These results were published in collaboration with my friend Professor Makoto and my friend Professor Juliano Antonio de Oliveira in EPL July 2020. So I thank you for your attention and acknowledge CNPq and FAPESP Brazilian agency for their support.